Cell 1. In this cell, we're diving into the essential aspects of chargeback forecasting analysis. This analysis is critical for businesses as it allows them to anticipate future dispute pressures, which helps manage financial risk effectively. The core of chargeback forecasting lies in predicting a few key metrics, such as the expected number of chargebacks over the coming week or month. By doing this, businesses can assess their potential financial exposure, which includes not only direct losses from chargebacks, but also fees and costs related to reversals. An important aspect of this forecasting approach is understanding how these charges can impact overall revenue, especially when considering refunds and the costs associated with representment. Moreover, it's vital to recognize that card networks like Visa and MasterCard maintain strict thresholds when it comes to chargeback ratios. If a business exceeds these thresholds, it opens itself up to a range of consequences, including penalties, increased scrutiny, and even processing restrictions. Therefore, proactive forecasting becomes a strategic asset, enabling companies to monitor whether they are trending toward a potential threshold breach. In addition to financial risk management, effective chargeback forecasting is a linchpin of operational planning. Increased chargeback activity can lead to a surge in customer support tickets and necessitate a larger response from dispute resolution teams and fraud management. Thus, understanding future dispute volumes becomes key for adequate staffing and prioritization, allowing teams to prepare effectively for what lies ahead. As we move on to the next cell, we will likely explore specific methodologies or models to quantify these predictions, delving deeper into the mechanics of chargeback forecasting. This will enhance our understanding of how to implement these strategies effectively in real-world applications. Cell 2. In this cell, we're diving into the strengths and limitations of using profit for forecasting, particularly in the context of predicting chargeback counts. Understanding these aspects is crucial because they help us recognize when to employ profit effectively and when it falls short, guiding us toward more advanced models like XGBRegressor and XGBClassifier. Profit is particularly appealing for quick, initial forecasts. It excels at modeling strong seasonal patterns, making it user-friendly for those without an extensive feature set. The strength lies in its ability to generate interpretable visualizations and timely forecasts. However, it's vital to note its limitations. Profit relies solely on date and the chargeback count, which means it doesn't take into account essential operational drivers, such as transaction volume fluctuations, promotional activities, fraud pressures, or even delays in delivery. As we transition to using models like XGBRegressor, the aim shifts to creating a more nuanced prediction of chargeback counts by incorporating those real-world drivers. This step is significant because chargebacks are influenced by various factors beyond seasonality, including transaction volume, risk scores, and even shifts in product mix. Moreover, the introduction of XGBClassifier allows us to explore a binary prediction framework. Instead of focusing solely on exact chargeback counts, this model enables us to determine strategic actions, such as assessing whether the next day will likely see a spike in high-risk chargebacks. Together, these models facilitate a comprehensive approach to chargeback forecasting. They cater to different but complementary business needs. While the numeric forecast addresses how many chargebacks might occur, the classification model focuses on actionable insights, essentially asking whether we should take preemptive measures. With this foundational understanding established, the next cell will likely delve deeper into implementing these models, setting the stage for building a robust forecasting system that combines both numerical and categorical insights. Cell 3. In this section of our Jupyter Notebook, we're generating synthetic daily data that simulates various factors affecting chargeback rates over a 2-year period. This simulated dataset is crucial, as it helps us understand the underlying mechanics of chargebacks and allows us to explore how different variables influence this financial metric. To begin with, we set up our random seed, which ensures our results remain consistent every time we run this cell. We then create a date range spanning 730 days, equating to about 2 years, and build a data frame to store this information. By adding the day of the week and month from our dates, we establish a framework that incorporates seasonality into our data. Next, we simulate transaction counts, incorporating cyclical patterns such as weekly and yearly variations, all while adding some noise to better mimic real-world unpredictability. It's crucial to note that we've capped the transaction counts to avoid unrealistic values, ensuring they remain within a sensible range. We also introduce promotional days into our dataset, which can cause spikes in chargebacks. This is a key aspect of our simulation that adds complexity by influencing the fraud pressure index and delivery issue index. These indices reflect potential fraud and delivery concerns, respectively, both of which can affect customer behavior and chargeback rates. The actual chargeback rates are then calculated based on a mixture of these various drivers, along with the event of weekends, which we've accounted for by slightly increasing the chargeback likelihood on those days. The result will be a rate that varies from day to day, reflecting real-life conditions. Using Poisson distribution to generate the actual chargebacks from our expected counts gives us a realistic representation of data that we can analyze. Finally, we define what constitutes a high chargeback day, marking any day where chargebacks exceed the 90th percentile of our synthetic data. This threshold is printed out for our reference, and we also display the first few rows of our data frame to visualize the data we've created. Looking ahead, the next cell will likely delve deeper into analyzing these chargeback patterns and exploring predictive modeling to better understand their implications. Cell 4. In this cell, we are diving into a practical example of using the profit library to forecast daily chargeback counts. This process is crucial because accurately predicting chargeback trends can significantly aid in financial planning and risk management for businesses. To begin, we prepare our data by extracting the relevant columns, specifically the date and the values we want to forecast. This setup is foundational, as profit requires a specific format, where the date is in one column and the corresponding values in another. Next, we perform a train test split, where we define a cutoff date that separates our historical data into training and test datasets. This cutoff is strategically set to 60 days prior to the latest date in our dataset, allowing us to evaluate our model's performance on unseen data. After splitting the data, we initialize the profit model, setting it up to consider yearly and weekly seasonality, important factors given that chargebacks may fluctuate based on these cycles. However, we choose to exclude daily seasonality, which makes sense in this context, where daily trends might be less informative. Once the model is fitted to the training data, we generate future dates for predictions, extending out for an additional 60 days. The resulting forecast gives us predicted values along with uncertainty intervals, which are essential for understanding the range of possible outcomes. To evaluate our model's performance, we merge those predictions with the actual values from our test set, allowing for a direct comparison. Using the root mean square error, we quantify the model's accuracy. A lower error indicates a more reliable forecast. As you examine the resulting RMSE, it becomes clear how well our model is performing. This evaluation helps us identify any adjustments needed for future analyses. Looking ahead, in the next cell, we will likely explore advanced techniques to refine our model, or even visualize the forecast to better understand trends and anomalies in chargeback data. Cell 5. In this cell, we're crafting a visual representation of the forecast generated by the profit model, an essential step for interpreting the predicted values alongside their uncertainty. This visualization not only highlights the forecast, but also provides critical context about the range of predictions, giving us a clearer understanding of potential outcomes and trends. We begin by importing the necessary library, Plotly, which allows for interactive graphing. The first major task here is the addition of the uncertainty interval, represented by two lines that define the upper and lower bounds of the forecast. These are created using the y-hat upper and y-hat lower fields from our forecast data. It's great to note that we use these lines in a staggered fashion. The upper and lower lines are drawn without visible strokes, yet they're effectively connected by shading, creating a filled area that visually indicates the uncertainty specific to each date. Next, we add the forecast line, which reflects the predicted chargebacks as defined by the y-hat variable. This is what we'll focus on most, as it represents our best estimate of future values. Notably, learners should remember that including actuals in this graph is optional. If you have a data frame that contains actual chargeback data, you can also visualize this alongside the forecast, which could further enrich the analysis, especially when comparing predictions to reality. As we proceed to configure the layout, we personalize the chart with titles and axis labels that make it clear what data is being represented. The dimensions of the graph are also carefully set to ensure readability and engagement, providing enough room for all elements without clutter. In the next cell, we will likely delve into interpreting this visualization, analyzing trends, and making informed decisions based on the insights gleaned from our forecast. This will help us understand how to leverage these predictions in practical applications or further analysis. Cell 6. In this cell, we're diving into data visualization by utilizing Plotly Express to illustrate two key aspects of our forecast: the trend over time and the weekly seasonality of our data. Visual representations like these are crucial as they can reveal patterns that might not be immediately obvious in raw numbers, providing a clearer understanding of trends and seasonal effects. The first part of the cell creates a line graph that displays the trend identified by the profit model. Here we're specifically plotting the dates on the x-axis against the trend values on the y-axis. It's essential to take note that updating the layout with features like hover modes enhances the interactivity, allowing users to explore data points effortlessly. This contributes to a more engaging user experience, as it presents critical information without overwhelming the viewer. Moving on to the second part, we start by generating a week's worth of dates that serves as our forecasting timeline. By creating a data frame with these dates, we can then apply our model to start predicting values for that week. It's important to keep in mind that the model's accuracy heavily relies on the data it's been trained on, so ensure you've prepared your data effectively prior to making these predictions. Following this, we extract the day names from our dates to visualize the weekly effects. By organizing the days of the week explicitly from Monday to Sunday, we ensure that our plot respects the natural order of the week, which is particularly useful for displaying seasonality patterns accurately. Sorting by day names makes the trends clearer, allowing viewers to easily spot the variations in weekly behavior. Finally, we create a line graph that highlights the weekly effects, integrating markers to emphasize individual data points. The dimensions of the graph are adjusted to provide a more suitable viewing experience. Such visualizations not only make the data more digestible, but also provide invaluable insights into how trends fluctuate across different days. Looking ahead, the next cell will likely build on these visualizations by introducing analytical methods to interpret the patterns we've observed here, potentially diving deeper into how to leverage them for actionable business decisions or further forecast improvements. Cell 7. In this code cell, we're diving into the analysis of yearly seasonality by generating a time series of daily values for the year 2025. This step is crucial because it allows us to visualize and understand how different days throughout the year can influence our data, particularly in the context we're working in. The first action here involves creating a date range that spans all 365 days of the year, which we store in a variable called year days. By creating this range, we can ensure that each day is accounted for in our analysis. Next, we place these dates into a data frame called year df, where we specifically label the column with ds to represent dates, as is common in time series analysis. Following that, we utilize a forecasting model, represented by m.predict, to generate predictions for each of these days. This step is where the heart of our analysis lies, as it transforms our date entries into numeric predictions that help us gauge the seasonal effect across the year. We then add a new column to year FC that captures the day of the year for easier reference and plotting. The visualization comes next, where we use Plotly Express to create a line graph. The x-axis represents the day of the year, while the y-axis showcases the predicted yearly effect. By doing this, we can clearly see trends and variations over time, which may correspond to seasonal behaviors. It's important to ensure that our model has been adequately trained on relevant historical data to make these predictions reliable. Otherwise, we might encounter misleading patterns. The final step involves adjusting the plot's dimensions for better visibility, which will ultimately enhance our overall understanding. As we look forward, the next cell will likely build on this analysis, perhaps focusing on interpreting these seasonal trends or integrating them with other data layers to draw further insights. Cell 8. In this cell, we're preparing our dataset for time series modeling and fitting two different regression algorithms, XGBoost and random forest. This is crucial because it allows us to predict future chargebacks based on past data, utilizing both historical trends and multiple features. To begin, we create lag features, which are essential for time series analysis. These lag features, specifically designed to capture the values of the target variable at previous time points, will help our models recognize patterns over different intervals. We've implemented several lag periods, including 1 day, 2 days, and more extended periods like 14 and 28 days. Next, we introduce rolling features to summarize past behaviors over defined time windows. For instance, calculating the rolling mean and standard deviation over 7 and 28 days gives us a sense of how the data fluctuates over time. We further enrich our dataset by adding calendar features such as the day of the week and the month, which can provide additional context to the chargeback patterns. After crafting these features, we need to handle missing values caused by the lag and rolling operations. Dropping these rows ensures that our models only train on complete data. Following this, we define our feature columns, incorporating transactional metrics and our newly created lag and rolling features. The data is then split into training and testing sets, with the last 60 days reserved for evaluation. This time-based split ensures that we are simulating a real-world scenario where future data is unknown and must be predicted from past data. Having set up our features, we proceed to configure and fit both the XGBoost and random forest models. XGBoost is fine-tuned with parameters that optimize learning, assigning weights carefully to balance bias and variance. Meanwhile, the random forest model leverages multiple trees to improve accuracy and reduce overfitting. Once both models are trained, we make predictions on our test dataset. The performance of these models is evaluated using metrics such as mean absolute error and root mean squared error. This gives us a tangible sense of how well each model is performing in predicting chargebacks. Finally, we compile the results, including the actual and predicted values for a clearer comparison. This structured output will facilitate our next steps, where we will likely delve deeper into the performance metrics and potentially refine our models for even better predictive capabilities. Cell 9. In this cell, we're setting up a framework to predict future trends over the next 60 days based on existing data. This process is crucial because by understanding future drivers, we can make informed decisions and strategies. We begin by defining a variable, h, which represents the number of days we want to forecast. The logic kicks off with identifying the most recent date in our dataset, allowing us to create a timeline for the predictions that follows immediately after. Using this last date, we generate a series of future dates for the upcoming 60 days. This is accomplished through the PD-date-range function, which constructs a sequence of dates taking into account a daily frequency. Once we have our range of dates, we create a data frame named future to store these dates along with various predictions. It's important to note that some entries are currently filled with placeholder values, so they will need to be customized based on more specific forecasts or business plans. For example, we're naively estimating the transaction count by averaging the last 28 days, which operates under the assumption that past trends will continue. This could lead to misleading conclusions if there are significant shifts in the market or operational strategy. We also introduce an assumption that there aren't any planned promotions by initializing the promotional index to 0. Additionally, we're incorporating other important variables like the fraud index and delivery issue index, which are again based on the averages of the last month. Each of these inputs can have a substantial impact on the overall prediction accuracy. Furthermore, we're including the day of the week and the month for each future date, which can be immensely helpful for understanding seasonal trends and weekly patterns. By displaying this future data frame, you're able to visualize the predicted framework that will inform the next steps in our analysis. In the following cell, we will likely leverage these forecasts to conduct deeper analyses, perhaps exploring how these predictions align with historical patterns or adjusting our strategies to enhance accuracy. This step forward will be critical as we refine our model and adapt to the future outcomes we've projected. Cell 10. In this cell, we're using Plotly to visualize the actual and predicted chargeback values over a specified time period, which is crucial for assessing the performance of our forecasting models. Visualization is an essential part of data analysis, as it allows us to see trends and discrepancies clearly, making it easier to draw insights from the data. The code begins by creating a figure object using Plotly's Graph Objects module. We then add 3 traces to this figure: the actual chargeback values, as well as predictions made by 2 different models, XGBoost and Random Forest. Each of these traces is plotted as a line on the graph, where the x-axis represents time and the y-axis represents the number of chargebacks. By using lines for each dataset, we can effectively compare how well our models forecast the actual values across the given time range. Another key point is the layout configuration. The visual presentation is enhanced with titles for clarity. The main title identifies the focus area, while the x-axis and y-axis titles contextualize what the viewer is inspecting. The hover mode set to X unified adds an interactive feature that allows users to gain precise insights at specific points in time, which can greatly aid in understanding the predictive performance. The width and height adjustments ensure that the output visualization is well proportioned, making it easier to interpret when displayed. It's worth noting that while the code is straightforward, ensuring that the data frames used have the required columns is essential to avoid runtime errors. Inconsistent data or missing values can lead to misleading interpretations. Looking ahead, the next cell will likely delve deeper into interpreting these visual results, perhaps leading to discussions on model accuracy or generating additional metrics. This will allow us to further refine our understanding of how well our predictive models are functioning and where improvements might be necessary. Cell 11. In this cell, we're visualizing the residuals, or errors, from our predictions to gain insights into how well our models are performing over time. By plotting these residuals, we can identify patterns indicating whether our predictions consistently overestimate or underestimate the actual values, which is crucial for model evaluation and enhancement. Here, we begin by creating a copy of our results, ensuring that we preserve the original data. Next, we compute the residuals for both the XGBoost model and the random forest model by subtracting the predicted values from the actual values. This calculation gives us a clear view of how far off each model's predictions are from reality, which we store as new columns in our dataset. We then prepare to visualize this information using a scatter plot. The x-axis represents time, while the y-axis shows the residuals. Adding two traces to our plot allows us to compare the residuals of the two models directly. Each trace represents the residuals for one of the models, giving us the opportunity to see how their error patterns evolve over the same time period. It's worth noting that while we're primarily focused on the residuals, this visual representation can tell us a lot about the model's performance and help us further diagnose any potential issues. For instance, consistent patterns in these residuals could indicate a systematic error in the model, suggesting that additional refinement might be needed. Finally, we fine-tune the layout for clarity and presentation, ensuring our plot is easy to interpret. As we move forward to the next cell, we'll build on these insights by exploring methods to address any detected issues in model accuracy, based on what we've analyzed here. Cell 12. In this cell, we are implementing classification techniques using XGBoost and random forest to determine whether tomorrow will be a high chargeback day. This task is crucial for businesses that want to proactively manage risk and optimize their operations based on customer behavior predictions. To begin, we first create a copy of our dataset, ensuring we do not alter the original data during our analysis. In defining what constitutes a high chargeback day, we rely solely on the training distribution. Specifically, we establish a high threshold by taking the top 10% of chargeback values from our training set. This statistical quantile sets a benchmark against which we can measure our subsequent predictions. Next, we extract the features and target variables to prepare for our classification tasks. The features, designated as XC, are derived from the specified columns in the data frame, while the target variable YC indicates whether a day is classified as a high chargeback day based on the threshold we previously determined. After segmenting our dataset into training and testing sets, we proceed to define our classification models. The XGBoost classifier is initialized with a balanced configuration, including parameters like a learning rate and depth of the decision trees, which are crucial for managing model complexity and preventing overfitting. Similarly, we set up a random forest classifier, emphasizing a larger number of estimators to enhance performance and stability in predictions. Both models are then trained on our training dataset. Once trained, we use them to predict the probabilities of a high chargeback day occurring on our test set. The AUC scores for both models are computed next, which provide insight into their predictive power. AUC scores closer to 1 indicate a model that performs exceptionally well. We then apply a threshold of 0.5 to convert probabilistic predictions into binary outcomes, allowing us to classify our test instances definitively. The classification reports generated for both models give a comprehensive view of their performance, detailing precision, recall, and F1 score, offering valuable metrics for analysis. Finally, we assemble the test results into a new data frame, while including the predicted probabilities for each model. This sets the stage for further interpretation. Looking ahead, the next cell will likely delve into a more detailed evaluation of these models' performances and present strategies for tuning and improving their predictive accuracy based on the insights we gather here. Cell 13. In this cell, we're implementing a predictive modeling approach that allows us to forecast future values and associated probabilities using historical data. Specifically, we utilize regression and classification models to make these predictions iteratively, which is crucial for understanding future trends in our data. We begin by establishing a framework for our forecasting. The first function, forecast_y_iterative, takes historical data and future drivers as input, alongside a trained regression model. Here, we're particularly interested in how the past influences future values. For each future date, we compute lagged features, which are historical values shifted backward in time, to incorporate them as predictors. This is an essential step, as it allows us to leverage the latest trends from the historical Y data to inform our predictions for the future. Next, we calculate rolling features such as mean and standard deviation over a weekly and monthly window. These statistics provide important context about recent performance and variability. After preparing these predictors, we utilize the provided regression model to generate predicted future values, appending each new prediction to our growing history. This iterative approach ensures that our future forecasts are informed by both historical trends and previously predicted values. The second function, forecast high proba iterative, operates similarly, but here we focus on predicting the probabilities of high values rather than the direct values themselves. Using a classifier, we again compute lagged features and rolling statistics before making our probability predictions. This function also incorporates the predicted Y values from the first step directly into the forecasting process, enhancing its accuracy. We then create a data frame to represent future dates, initializing drivers like transaction counts and indices based on recent historical averages to guide our predictions. The final steps involve calling our two functions to generate the predicted values and probabilities for future dates. This is a sophisticated workflow that highlights the interconnected nature of our modeling approach, where outputs from one step feed directly into the next. In the upcoming cell, we will likely delve into visualizations and interpretations of these predictions, allowing us to assess their implications for business strategy and decision-making. This transition into exploring the results will enhance our understanding of the forecasting model's effectiveness in real-world applications. Cell 14. In this cell, we're exploring different predictive modeling approaches and understanding when to apply each one effectively. This is crucial for ensuring that our forecasts are not only accurate, but also relevant to the specific business problem we're tackling. We start with Profit, a robust tool that excels in scenarios where historical patterns in the data, such as trends and seasonal effects, are key to making predictions. It's designed to accommodate various types of seasonal variation, making it a reliable baseline when you have confidence in the recurring nature of your data. Next, we consider regression methods, specifically XGBoost and random forests. These techniques shine in contexts where you can leverage additional explanatory variables, such as transaction volume and fraud signals. Here, the focus shifts towards generating count forecasts. The presence of these explanatory drivers allows us to build more sophisticated models that provide a deeper understanding of the factors influencing our outcomes. Lastly, we move into classification approaches using similar algorithms. This is particularly important for operational decisions, like identifying high-risk days or when thresholds are exceeded, where timely alerts can drive necessary actions. The emphasis here is on binary outcomes that help businesses respond quickly to potential issues. Each of these methodologies has its strengths, and knowing when to apply them can significantly enhance the insight gleaned from our data. As we transition to the next cell, we'll delve deeper into practical applications of these models, examining how their unique characteristics can inform our forecasting strategies and decision-making processes. This will set the stage for implementing the chosen techniques and evaluating their performance in real-world scenarios. Cell 15. This cell marks the conclusion of our current analysis. It's crucial because it encapsulates everything we've worked on, emphasizing the significance of our findings and how they fit into the larger context of our project. Now, stepping back, we can appreciate how every preceding cell has been guiding us towards this endpoint. Throughout our exploration, we've incrementally gathered insights, applied various methods, and examined our data closely. The final output serves as a comprehensive representation of our efforts, showcasing the results of our computations and analyses. What we've seen so far is not just a collection of numbers or statistics, but a narrative built from our data. It's important to reflect on the decisions we made along the way, how we processed information, which variables we prioritized, and the assumptions that underpinned our findings. One of the key takeaways is that each step was intentional, allowing us to build a robust understanding of our subject matter. Looking ahead, this completion doesn't signify an end, but rather an opportunity for evolution. The insights gained here can propel us into more advanced analyses or broader applications. Whether we're considering further experiments or developing new questions, the groundwork we've laid in this project will be invaluable. In the next cell, we will likely expand on these findings or explore a related area, adding even more depth to our understanding. So let's prepare to carry this momentum forward into our next adventure in data analysis.